Okay, so hi guys, is the audio working? Can anybody let me know in the chat? Am I live by the way? Okay, right. So everything's working, right? Yeah, so this was a contest, Codeforces round 716, Division 2 by Mohammad Ihab. And I was doing really good, like till the first four problems I was doing really good. But like I'm pretty sure my solution to the fifth problem is also correct. But yeah, so probably I made some silly mistake and I wasn't able to fix it. So that resulted in me getting so many wrong answers. Let me just check somebody else's solution, what the solution was. Pretty sure mine was correct. Okay, I'll just wait for the editorial then. It hasn't been posted. Okay, anyway, so so today we'll discuss problems from A to D. And I think at least the first two problems were like really easy. Not the second problem. I think the second problem was not very easy if you're not good at modular arithmetic, etc. But it was kind of standard, and then like if you know modular arithmetic, it's not difficult. Okay, so let's see the first problem first of all. So it is perfectly imperfect array. So we want a non-empty subsequence such that the product of the elements is not a perfect square, right? So it is easy to prove that a single element will always work, because let's say if all single elements are perfect squares, so then if you multiply everything, obviously the product will be a perfect square, and then it wouldn't work. So obviously a single element will always work. So we just have to check if there's at least one element in the array that is not a perfect square, right? Yeah, that was pretty easy. That's what I did for this problem. There are multiple ways to do this. I made a set of perfect squares. So first of all, I made a set of perfect squares and I pushed all the perfect square into that set. And then I just find whether the input element is in the set or not. And if it is not in the set, then I print yes, because yeah, so that means one of the elements in the input is not a perfect square. And that gives us the answer. So that was the answer for the first problem. Okay, so let's see the second problem now. Okay, second problem is easy to think, but if you don't know modular arithmetic, then it might be a little problematic. But yeah, let's look into it. So basically what you have is, just a second. Okay, so baby, his first words were and, zero, and some big. So what you want is, you are given n integers. You are given two integers n and k, and you want to count the number of arrays of length n such that all the elements are between 0 to 2 to power k minus 1. That means the size of all the elements is k bits, and you want the bitwise and of all the elements to be 0. So basically, if you take the bitwise and, you can see the definition if you go to this page. I think this is the Wikipedia page, right? And out of all such possible ways, you want the sum of the elements to be as large as possible, right? So let's examine what this would look like. So let's say if you have k bits like this, it could look something like this, right? So to make the and 0, if you look at each bit separately, so if you look at each bit separately, this basically means that there's at least one 0 in each of the bits, right? But this 0 could be anywhere, and everything else has to be 1, because basically we want the sum to be maximum, I guess. Right. Okay, so we want the sum to be maximum. So that means all the other. Just a second. So yeah, these are the numbers. Okay, so these are the numbers like this. So I have 4 numbers here, and to get this sum maximum, obviously I want all the bits to be 1 except one of the bits at any place, right? So basically, if you use some simple combinatorics, you can put this 0 anywhere in this in these n places, and then you can put this 0 in any of these n places, and this 0 in any of these n places, and so on, right? Okay. So basically for each 0 you have n options. Okay. And there are k zeros in total. So the answer becomes n to power k mod 10 to power 9 plus 7. Okay. So you need to know how to do this, do things in mod 10 to power 9 plus 7. So basically this is something that if you know you can do it, otherwise you can't. Okay. Is Neil here? My stream fell off, CF. Thanks for letting me know. Okay, I'll fix it pretty. Okay, just a second. By the way, hi Neil, and congratulations on winning both Google Kickstart and also this round today. Okay, yeah. So thanks for reminding. Thanks for letting me know that it was off. Okay, yeah. Thanks. So anyway, so basically that's the solution. We just want n to power k, and you need to know how to calculate this in the modular field, right? So for this, again, let me show you my code. Okay, right. So this function that I used here, it's called the binary exponentiation, right? So this is a binary exponentiation function. You could have done it without this as well, because k is not very big, so k is just 20. So you could have multiplied n to itself 20 times, but you have to use modular arithmetic, right? So modular arithmetic is basically like if you want to multiply two numbers with each other, you take mod at each step. Otherwise, the answer will overflow. Okay. Yeah, so that's what we had to do here. Like if you knew, it was easy. Otherwise, you couldn't do it. Okay. And then we have this one, product 1 modulo n. Right. So I like this one a lot, and okay. Yeah. So I like this one a lot. This is actually very interesting, and you need to be familiar with number theory to understand the things that are going to happen now. Okay. Right. So basically, you are given. Okay. Yeah. So basically, you are given uh, n. Okay. So you are just given a single integer as input, that is n, and you want to find the longest subsequence of this array from 1 till n minus 1, whose product is 1 modulo n. So basically, you want the longest subsequence such that if you multiply all of the elements, the product is 1. And like not 1, it is basically a multiple of n. So if you take the remainder of the product with n, it is 1, right? So that's what you want. And this is just the definition of subsequence. So basically you want to pick the elements from there, and that's what you want to do. Okay. So the first observation here is that all the elements that we take must be co-prime to n. Okay. So all the taken elements must be co-prime to n. Okay. So why is this happening? Why do we want all of the taken elements to be co-prime to n? So I can show you with an intuitive example. Let's say n equals 8, and obviously this is a multiple of 2. So that means 8 is even. So let's say if we take any even element, so let's say if we take 6, then what will happen is whatever the product is, it will be a multiple of 6. And then when we take the modulo, like whatever the product is, so product will be a multiple of 2. So if the product is a multiple of 2 and n is also a multiple of 2, then p mod n will also be a multiple of 2. So obviously it can never be 1. So there's no way we will ever take any of the numbers that are not co-prime to n. Okay, so we will only take the numbers that are co-prime to n. And since n is not big enough, we can just check for each element one by one whether it is co-prime to n or not. Okay, so let's take this example with n equals 8. Right, so with n equals 8, we know the elements are 1, 2, 3, 4, 5, 6, 7, and we know that out of these elements are co-prime. So How did I count wrong? Okay, right. So we know that 2, 4, and 6 are not co-prime to 8. So we remove them in the beginning. And now we're left with 1, 3, 5, and 7. Okay. Let's do one thing. Let's multiply all of these and take the modulo 8. Okay. So if we multiply all of these elements, we get 7 times 15, which will be, I think, 95, I guess. Okay, I'm not that 105. Okay, right. Yeah, so we get something like 105, and is that equal to 1? That should be just a second. Right, so 105. Let's try to divide it by 8. So we get something like, yeah, obviously. So we get the remainder 1, right? So yeah, so this is working. So we're lucky that this works, and we will just take all of these elements. But what will we do if this is not equal to 1, if the product is not equal to 1, like in this case for n equals 5. So for n equals 5, we have the terms 1, 2, 3, 4, right? And none of them are not co-prime to n. So basically we will just take all of these, and if we multiply all of them, we get something like 36, I guess. Wait a second. 4, 3 is 12, 12 to the 24, right? So we get 24, and if we try to take 24 modulo 5, we get 4 instead of 1, right? So if we are lucky, then we can just take all of the elements. But what if we are not lucky? So what will we do then? Okay, then it is a smart observation that we need to make here, and that was the whole point of the problem. So that was the main thing of the problem. So you have to notice that this value, whatever product that you get, so basically P mod n, whatever P mod n you get, it is definitely smaller equal to n. It is definitely smaller than n, in fact, right? So P mod n is definitely smaller than n, because obviously it is mod n. If it is greater than n, we will just subtract n from it. So it is definitely smaller than n. And we also know that it is greater than 0, because if we take non-coprime elements and multiply them, obviously we cannot get a multiple of n, because like we don't have any factor of n in all of the numbers that we had. Okay, and apart from this, p and n are coprime. Okay, yeah, so this is an important observation. It is a bit hard to observe, but it is very easy to verify. So we know that any of the numbers that we multiplied, none of them had any common factors with n. So obviously if we multiply all of them, no common factors will appear. So that means p and n will be definitely coprime. So how will we use this information? So we can use this information by knowing that we got p by multiplying all of the coprime numbers in this range. So we took all of the coprime numbers, we took all the numbers that are coprime to n and were in this range between 0 to n, as was given in the problem. The range was 1 till n minus 1, right? So if we take all of these elements and multiply them, and the result is just one of such elements that we took initially, what we can do is we can simply remove one of the elements that is equal to the product. Okay, so too much words, let me explain with this example only. Okay, so we multiply all of these, we get 24. 24 mod 5 is just 4. Okay, after that we know that 4 lies in this range between 0 and 5, and we also know that the GCD of 4 comma 5 equals 1. That means 4 and 5 are coprime. So if 4 is in this range and is coprime to 5, that means definitely we initially multiplied it to get the product P. And now what we will do is we will just remove this element, and now what we get is a bunch of elements which multiply to give 1. So you can see that 3 2s are 6, and 6 mod 5 equals 1. So yeah, so basically we try to take all of the non-coprime elements, we take the product. If that is 1, that is fine, but if it is not 1, we just remove the element that is equal to the product, and it is guaranteed that that element will definitely be present in the elements that we initially multiplied. So yeah, so that this was a nice question. Let me show you my code. Okay, so I took n as input, then I took the vector c, which is basically storing the non-coprime values. So yeah, so if the GCD of I and n is equal to 1, so I put it in the vector which contains all of the non-coprime values, and I also multiply I to p. So now I have like I'm just building this product of all the elements in the vector. So if it is 1, if the product is 1, then simply just print all the elements in the vector. But if it is not 1, then what we will do is we will try to remove one of the elements that was causing the problem. So basically, if the element x is equal to the product, we just continue. Otherwise, we will put everything in the vector. And yeah, so everything else we will put in the vector and we'll print that vector. Yeah, that was the solution. Let me see the chat for now for a little bit. Why only one element? So yeah, so we're removing only one element because we want to find the longest subsequence. And what I just proved is it always suffices to just remove only one element, right? So after we take all of these elements, there's no way we can take any extra element. There's no way we can replace any element. All we can do is remove some of the elements. And if we can remove just one element, it is always beneficial, more beneficial than removing two or more elements, right? So that's why, since I proved that you can always do it by removing one element, you can definitely be you can definitely be sure that the answer will be just one less than the vector that you initially found. What will be the occurrences of p mod n? Yeah, it will occur one time in the array because all the elements are distinct. This was hard for someone who doesn't deal in number theory for sure. Yeah, I agree. So I think most of the context was a bit toward the math kind of things. So like if you're good at maths, you can do it. Okay, by the way, so now I'm going to move on to the problem D, and I would really like to know in the chat uh, if somebody solved D. I really wanted to. I really want to know your approach for that. My approach is actually a randomized solution. So okay. You use square root decomposition for D. Actually, I made a randomized solution. So basically, I used a randomized solution to find the mode. We had to find the mode in this problem. Like as far as I know, we had to find the mode, but I'm not very sure. But yeah, so everybody used square root decomposition. Tried to use Mohs algorithm. Mohs algorithm. Oh right, I think yeah, I think Mohs algorithm can work. Oh, maybe Mohs algorithm was intended here. Yeah, you just have to keep track of the maximum frequency, right? Yeah, I think the intended solution was Mohs algorithm. So I'll explain that. But what I did is a randomized solution, and this is like much more interesting than the Mohs solution. Although it can still fail because, as I said, it is a randomized solution. But yeah, like there's something really interesting to learn here. So even if you were able to solve this problem using some alternate method, I would really recommend you learn this method as well, which I'm going to discuss right now. Okay, Mohs is same as square root decomposition. I think in a way, like the time complexity of Mohs is n root n plus q root n, something like that. So yeah, it is a form of square root decomposition. So basically, square root decomposition is a more general thing, and Mohs is a specific case of that. Okay. Again, so in this problem, what I did is I used a randomized solution, but but before we get into that, let's reduce this to a simpler problem, and then we will see what kind of method or data structure or technique we can use to solve that. Okay, so let's try to reduce this to a simpler problem. So basically what I did is, we are given a lot of elements in the array, and then the query is basically a sub-array, and what we want to do is we want to partition the sub-array into multiple pieces, multiple subsequences, and in none of the pieces we want any of the value to occur more than steal of x by 2 times, right? So it's something like, if the size of array is equal to right? So let's say if the size of array is 1, then the mode frequency that is allowed is 1. If the size is 2, then again the mode frequency that is allowed is 1. Here also, here it is 2, then here it is again 2, then 3, 3, and so on, right? So basically, if you have what this means is, if you have, let's say, 6 elements in the array, the maximum frequency of any element cannot be more than 3. If you have 5 elements, then also the maximum frequency of any element cannot be more than 3, because steal of 5 by 2 is nothing but steal of 2.5, which is 3, and that means more than 3 elements are not allowed. Okay, so what do we do in a case when a certain element has a very high frequency? So let's say if we have something like 3, 3, 3, 3, 3, 2. Okay, so if we have an array that has a lot of 3s, and obviously we can see that the number of occurrences of 3 is much more than the allowed frequency. So what should we do here? Obviously we will partition this into multiple subsequences, and the smartest way to do is to put the 3s in a single subsequence alone, and we cannot put 2 3s together, because with a subsequence of size 2, only the mode frequency of 1 is allowed. So obviously we cannot put 2 of them together, and we have to separate them alone, right? So something like so this has to go in a separate subsequence, this has to go in a separate subsequence, this also in a separate subsequence, and then these 3 are allowed in a single subsequence, because for an array of size 3 the mode can be 2, like the frequency of the mode can be 2, right? So that's what we want, and now the problem kind of reduces to a very simpler thing. So what we want to do is, we want to find the frequency of mode in a given range. Okay, so let's say you are given a range in an array, like let's take this array for example, 1 3 2 3 3 2. Let's say if you have 1 3 2 3 3 2, okay, and then you are given a query. So let's say this is the query that you're given. So you want to find the frequency of mode in that in this array, right? So we know that 3 occurs 3 times, so the mode frequency here equals 3, right? And that's what we find, and that's what we have to find. After that, we just like after that it is easy to get the answer. To do this, I basically used binary search to see the minimum number of elements that we have to put in a separate array, and yeah, it worked. There might be some O1 formula also. I wasn't able to come up with it because I was trying to be really quick, but yeah, so with binary search I was able to do this. And so the main problem that is left right now is to find the mode frequency, or to find the mode itself, right? So as I saw in the chat, the solution that people are posing is to basically find the mode or the mode frequency using Mohs algorithm, the Mohs algorithm. I won't cover this deeply because this is not a very trivial kind of thing. So maybe I'll make a video on this somewhere later in the future. But yeah, with Mohs algo you can kind of do this, because yeah, so basically this runs in n plus q root n time, and it can solve queries like this. So it is more like a optimized way of doing two pointer kind of thing. So you just have to keep the frequency of all the elements, and you have to keep track of the maximum of all the frequencies, right? So yeah, so that's what we want to do here. I think you will also need a set in which you put all the frequencies. So maybe you'll have an additional log here. I think this can be too slow, but I'm not sure. People are saying it worked for them. So yeah, that's good. But I'll tell you my solution, which was like really, really cool according to me. Okay, so the cool solution here is, okay, so this is like a very cool solution. Even if you don't, even if you're not very good at competitive programming, even if you weren't able to solve B or C or anything, you'll still like this very much. And yeah, this is, so as I said, this is like a very, very cool solution. And yeah, so I used randomization here. Pretty sure most of the people will like this a lot. Randomization. Okay, right. So first of all, I noticed that we don't need, so the thing that I noticed is we don't need the mode frequency if it is smaller than like width by 2. Okay, so width means the width of the interval that we are finding. Okay, so basically, let's say uh, if we have an interval from 2 to 5, so obviously the width is 4, right? So if the mode frequency is less than width by 2, we don't care about it, because like then we won't make any partitions, right? So we care about it only if like the mode frequency is greater or equal to width by 2, right? So what this means is, if we have like what I'm trying to say is, if we have 6 elements here, at least 3 of them have to be equal to the mode. Otherwise, I don't care what the mode is, right? So what this means is, in the range that I have, at least half of the elements are equal to each other, right? So if at least half of the elements are equal to each other, let's say we randomly pick an element. Okay, so randomly pick an element. So if we randomly pick an element, then the probability that like assuming that there is at least one element with frequency greater or equal to half of the width, then the probability that the element that we pick is mode will be greater than 1 by 2, greater or equal to 1 by 2. So the probability will be greater or equal to 1 by 2, right? So the probability that if we randomly pick an element and it is equal to the mode is greater or equal to 1 by 2, given that there are at least half of the like at least half of the elements are equal, right? So the probability is greater or equal to 1 by 2. But what if we repeat this experiment multiple times? So what if we repeat this, let's say 20 times? So if we repeat this 20 times, then the probability that at least one of the element that we pick is the equal to the mode is equal to 1 minus 1 by 2 to power 20, right? And this value is like, this value is huge. So it is like a very big value, and the probability that you do not find the mode, if even if you try to find it 20 times, is like very, very low. And it's kind of like almost impossible that this would actually happen to you, right? So yeah, that's why just by randomly picking 20 elements, you can be sure that you will find the mode. And then after that, you take all of the 20 elements, check for each of them if their frequency is greater than the width by 2, and then yeah, that's the mode frequency, and you have found it. Yeah, basically that's what I did here. I personally think this was a cool solution, and you can see that this got accepted also. So I didn't have to, I didn't get a wrong answer. That's what my point is. Okay. So yeah, so you can see basically that's what I'm doing here. I have a random number generator. So by RNG, I mean the random number generator. And then this random number generator has a I'm basically, this line means that I'm finding the numbers uniformly randomly between the range L and R, right? So each number is actually equiprobable, right? And then what I'm doing is I'm running it actually 22 times, like 20 times would have been enough, but okay, so I'm running it 22 times. And what I'm doing is each time I'm finding a random element and I'm putting it in a set, okay? And then I will just go through the set and try whether try to run this code with each element assuming that it is the mode, and then I just have to find the frequency of that element in this given range, and I can do that using upper bound and lower bound. So initially I had a vector which stores the indices of all the occurrences of a given element. So using that and this lower bound and upper bound, I can easily find the frequency of that element, and I'll just take the maximum frequency. And yeah, after that it is quite easy. I just binary search to find the number of extra arrays that I have to make, and yeah, so basically when I add 1 to it, that is my answer. So yeah, so that concludes my solution. Okay, so if you have any thing to say right now, you can write that in the chat, because I'm reading the chat right now. Oh, editorial. Let's see if they gave the. Okay, see, they have also given the randomized solution in the editorial. Yeah, so basically this is what I used in my code. Okay, and this is the, I think this is the Mohs algorithm solution, which is which is definitely tougher. So if you can kind of come up with the randomized solution, that is like a very cool thing. And then they also have a deterministic solution. So I think this is the range mode query thing. It was present in some blog, but that was like a very difficult. I don't know what this is. Yeah, we split it into 2 ranges, and then this element must be in the super frequent. Okay. Right. So yeah, this is some deterministic solution. I'm not in the mood to analyze this right now. Okay. Any ideas how to get the O1 solution? Yeah, even I was wondering how to find the O1 solution. Hmm. I think I think this is the O1 solution. 2 times F minus M, I guess. I don't know how they came up with it, but I just use binary search because uh, that actually took me less time to type out the binary search than actually trying to come up with an O1 solution. So I decided not to try it, and I just wrote the binary search. I also wanted to see the solution to E. Uh, yeah, looking at this, I believe my solution was exactly this. I have no idea why it failed. I really want to see the system tests, the hidden tests on which my code was failing. Can I see them now? You cannot see them? Okay. Yeah, I'm not going to discuss my solution because it could be wrong, but I'm pretty sure that there was nothing wrong here. Must be a silly mistake, but probably it was correct. Okay. Am I late? Yeah, I think you're late because we're. I think we're done with this stream. I'll just answer some things from the chats. From the chat, if you have any questions, you can just ask those. I'm reading the live chat right now. Hi Samuel. Can we use sieve in problem C? Why would you need sieve in problem C? Why would you actually need C for problem C? I think problem C was just about finding the coprime numbers, so I don't think you need C. How you did C so fast? I don't know. It was pretty obvious. Like I knew that modular inverses don't exist for non-coprime for the non-coprime elements, right? So we only take the coprime elements. I think everywhere in the editorial I said non-coprime while it was coprime. Okay. Even Wilson's theorem. What is the Wilson's theorem? Oh right, I know this. Yeah, I know this because like each element has the. I think this only works for prime number, right? This works for a prime number because then all the all the elements get paired up with their uh, modular inverse, and then only n minus one is remaining. That gives you congruence of -1. Did you do the bonus for C? What is the bonus? Oh, solve it for n smaller equal to 10 to power 12. N smaller equal to 10 to power 12. I think in this case, first of all, we need the product of all the coprime elements, right? So we need the product of all the coprime elements. Okay. And once we do that, I'm not sure about it right now. I don't know how I will be able. I don't know how to do it right now. Moreover, we definitely cannot print the like obviously we cannot print the number of we cannot print all of the values because there can be a lot of values. So maybe we just have to print the number of values, right? And how will we print the number of values? So basically we just have to check if the product that we have is equal to 1 or not, right? Yeah, that's what we want to check. We want to check whether the product of all the elements is equal to 1 or not. And I think maybe we can do it without actually finding the product. But I'm not sure about it because first of all, or maybe it is something like we take something like n factorial and then divide it by all of the non-coprime elements, I guess. Not sure. Yeah, I can't think of this bonus task right now. Has anybody answered that in the comments? And I'm just waiting for the system test to get finished. Is it over? Okay, yeah, is it over? It's over. I really want to see the test case on which my code failed, or at least the verdict. Wrong answer. Guessed incorrectly. Okay. Okay, yeah. So maybe then it's a error in the logic. Yeah, I'll look into it later. So what's going on in the chat? Delete only prime factors. I don't think we only delete the prime factors. Like we do delete the prime factors, but so let's say if we have the element equals 8 and so we remove 6, right? So we divide 3 as well. So like if we have to remove 6, we divide both 2 and 3. How will we know how many times we have to divide the 3? Because 2, I understand 2 is just a prime factor of multiples of prime. Product of integers relatively prime to n congruent. Okay, you have a link here. Let me find it. product of integers relatively prime to n mod n. Wow. Yeah, so this is always plus minus 1. Okay. Okay, that makes sense, but every number is relatively prime to n and can be paired up with its multiplicative inverse. Yeah, I think I disagree with this one. Hmm. Yeah, I'm not going to read it right now. It seems a bit complex. Okay. The graph has an Hamiltonian path. I think I found it. And what do they do after finding the Hamiltonian path? Every edge that goes in a forward is useless since you can just walk down the path itself. Yeah, that makes sense. And now with a few more edges, we can form all paths. So we use 2 pointers. I mean, what I did is exactly the same thing. Like I exactly did this exact same thing. I even asserted that I have found the Hamiltonian path. I have no idea why this didn't work. Hi, Sanskar. If n is prime, then we simply print from 1 to n minus 2, and otherwise we will never have to remove an element. That seems like I don't know why that would happen. In problem C, why does removing p mod m from p makes new p mod m equals 1? Yeah, you're just dividing the inverse of p on both sides. So it is like you're just dividing the inverse of p on both sides, Alberto. And we know that the inverse will exist because we know that p and n are co-prime. So we know that we can be guaranteed that the inverse will exist. That is from the Wilson's theorem. Okay. Maybe there is a extended thing here. Like they only say for prime numbers, they have no, like they don't say anything for composite numbers. I don't know. I'll look into it later. It's used as a primality test. Okay, yeah, no point. How did you wake up so early for Kickstart? Yeah, actually I didn't sleep all night. That was easier than waking up that early. Okay, so I guess I'm going to end the stream now. We have had all the discussions that we were going to have. Okay, so thank you for watching everyone, and good luck.